All right, congratulations on making it through quantum mechanics. Now we can kind of move on to back to kind of a little bit easier chapter, one that's more about less about a skill and the abstract and more about just memorizing some facts and and just knowing some stuff. And so that's what this chapter on the periodic table is all about. So this lesson we're looking at the history and structure of the periodic table and why, and kind of once again we're looking at a little bit of the history of that structure and so on. So history of the periodic table. So during the 1800s, the number of elements doubled from 30 to 1600. It's really during the early 1800s. And so, because prior to the 1800s, all they knew were these yellow and green elements. Those are the only elements that were known. You can see about half of them were known before 1600 even, like iron and copper and zinc, the metals that spawned, the Grecian and the Roman empires, and carbon and making steel and tin and lead. And so some of those common things. And then after that, we get some of the yellow ones. But as we start getting into 60 plus elements, things start getting a little more confusing, and scientists were looking at ways to classify and organize things, because that's what scientists do. Think about like Mendel and genetics and trying to organize things. And you think of taxonomy in biology, trying to organize things. So that's what scientists do. So at the time, they knew about atomic weights as well as chemical and physical properties. So that's what they're trying to use to organize things. Because remember, atomic number doesn't come along until Chadwick in the 1920s. And so that's not really helpful 100 years before then. So 1829, Dobrainer, or Daubreiner, I don't know how you would say that in German, not my best language. So he placed the elements in groups of three called triads, and they were based on similar physical and chemical properties. That's going to be kind of the theme, that scientists noticed that certain things had similar properties, reacted similarly or behaved similarly, and so they wanted to kind of look at that. So he came up with these triads: lithium, sodium, potassium. They all react violently with water. Calcium, strontium, and barium, similar but not as strong. And then like sulfur, selenium, and thorium, they're very smelly, nasty things, and so on. So they had all these things. So this didn't really stick. So, fast forward 35 years, you get John Newlands comes along, and he says, hey, wait, I'm seeing a pattern where things seem to repeat every 8 elements. And so he called this the law of octaves. And this is a picture of his law of octaves. Now, a couple of problems with this. It only worked a little bit. If you look at the periodic table, it really works really well for the S&P block in the second and third periods, or second, third rows. But it fails when you start getting down in transition metals, and it doesn't quite work super well that way. That was part of his problem. Also, it was a problem because he used a musical term, octaves. And so it just didn't really connect with people. So everything comes down a couple years later, 5 years later. Dmitri Mendeleev published what is considered the first modern periodic table. And even though Mendeleev to me kind of looks like a creepy kind of guy, he was brilliant. Perhaps that oftentimes go together. A little crazy and a little brilliant go together. So Mendeleev arranged them based on repeating patterns of properties, and he didn't care whether the masses lined up or not. He wasn't going to be enslaved by one property when he was trying to get all the other properties to line up. Because there are several places on the periodic table, like copper and zinc, where zinc is lighter than copper, but they're in opposite order. Once again, we didn't know about atomic number yet. But Mendeleev's just saying something's not working here, so I'm not going to worry about atomic masses. I'm just going to put them where they belong. Atomic masses help, but he's not letting it be the end-all, be-all. And so the other thing he did that was just, this is the part that blows me away. Not only did he say, I'm going to ignore atomic mass if it doesn't match up, but I'm also going to say, hey, wait a second. There should be something here that fills this gap because it's not my patterns falling apart. So I'm just going to assume that we're going to discover something that fills this gap to make my pattern work. And then not only did he do that, he then proceeded to predict the properties of these things. So for example, we didn't know what gallium hadn't been discovered yet. And so he skipped gallium space, and he called it eco-aluminum, meaning beyond aluminum, or I think it's something like beyond aluminum. So, because it was underneath aluminum on the periodic table. And he predicted its atomic mass. He said, hey, it's going to have an atomic mass around 68. Oh, well, 69.9. Yeah, a little off, not too bad. Well, melting point, 29.8 degrees. You can melt gallium in your hand. That's a very low melting point for a metal. Density, that one he got on a little bit more dead on, and he was able to predict how it would react and form formulas in compounds, oxides specifically. And so he did this like repeatedly. And so that's part of his genius in creating his periodic table. So that's part of why he's considered the father of the modern periodic table. So atomic number comes along later. As we learned in the atomic unit, Rutherford discovered the nucleus, but he couldn't figure out how to count the neutrons consistently. So that came along later with Moseley, who used X-rays to accurately, consistently count protons. And that gave us atomic number, and that way everything managed to match up with Mendeleev's arrangement. I mean, once again, we're talking, 50 years later. Kind of like, almost like Einstein with relativity. Like, Mendeleev said this, hey, this is how it needs to work. And it wasn't until 50 years later they were actually able to prove and match it up using atomic number. That's part of his genius with it. So that's the history of how we get to the periodic table we have. Now, what's amazing actually is the structure of the periodic table and how it's going to match up with everything we've learned to this point. So there are a lot of different ways to look at the structure. So the first way you got to know are groups and periods. So groups are the columns on the periodic table, and each group has similar properties. Okay? And then periods are the rows. So groups are the columns, and periods are the rows. So part of the reason why these are called periods is because something that repeats on a consistent pattern is periodical or has a period. And so every time you get to the end of the period, you get to a noble gas. They have similar properties. And then every time you start a period, you're back in group 1, which all have similar properties. And so there's a repeating pattern of properties, and that's why they call them periods. So we can also look at S, P, D, and F blocks. We saw this in the previous unit, where we got our S block over here, groups 1 and 2. Groups 13 through 18 make the P block. Groups 3 through 12 make the D block, and then these guys down here make the F block. And so we've seen that before. It matches up and works really, really well. All right, so it is the similar electron configurations within a group. That's why they have similar properties. So for example, when we look at the group 17, they have similar properties because all of them end in P5. And later on we'll learn about something called valence electrons. They all have the same number of valence electrons. They all behave chemically very similarly. They make salts with group 1. They're highly reactive. They're toxic and for that reason make good sanitizers. And use iodine to clean cuts, that kind of thing. Use chlorine in pools. And so they all have very similar properties, and it's because of their electron configuration. Another way we can break up the periodic table is into what we call representative and transition elements. Representative elements are the S and P block. We call them representative because they have consistent properties that don't change. So they have things like where their charges stay the same, they react the same, they don't do anything weird. In contrast, the D block is called transition metals, and they tend to be a lot more complicated because, as we'll see later when we get into ionic nomenclature, they can have multiple charges, and they can bond differently than the representative elements. They also, that D block, those D electrons can come in and affect how they bond. That's more of an AP Chem college chemistry topic, but they get a lot more complicated. And then the intertransition metals are even different. That's the F block. Okay, they're called the intertransition metal. All right, so that's how that's broken up. So S and P block are your representative, D block is your transition, and then your F block is your intertransition. All right, and then another one that's really, really critical and really, really helpful is metals and nonmetals. So if we took a staircase and we drew it through the middle of the P block, like I've drawn here. If we look at the staircase, everything to the left of the staircase, with the exception of hydrogen, is a metal. So as you can see, 2/3 or even more of the periodic table is considered metals. Everything on the right side of the staircase is considered a non-metal. Add hydrogen. So hydrogen sometimes drawn over here. Sometimes helium is drawn over here for quantum purposes. And so, but these are all non-metals. I think it's pretty obvious that hydrogen, being a gas, is a non-metal. So these are all your non-metals. And then these guys touching the staircase, with the exception of aluminum, and then even acetine and tennessine. So and then these things which are touching the staircase, they're called metalloids or semi-metals. And they are kind of, as would be implied, they're kind of the thing that is the transition between metals and non-metals. And they have properties kind of in between. So just kind of writing that out in words for you. If we draw a staircase, on the right side is the non-metals, on the left side is the metals, and then touching the staircase are the metalloids, with the exception of aluminum. Alright, so let's look at properties of metals and non-metals. So properties of metals. Metals form positive ions. That's going to become very important later. Luster, it means they're shiny. Think about your metals, your gold, your copper. Now they can get chemical coatings on them that make them dull, oxide coatings, but for the most part they are shiny. They're also known for being malleable, which means they can be pounded into thin sheets without breaking. Think aluminum foil, gold foil, things like that that are common for metals. In addition, they can also be pulled into thin wire without breaking. That is called being ductile. All of our wires are made out of metal. We don't make, sulfur wires because they wouldn't work very well. They're very good conductors of heat and electricity, and they are solids at room temperature with the exception of mercury. All right, so in contrast, nonmetals are kind of pretty much the opposite on everything. They form negative ions, no luster, no shine. They're just usually flat. That's if they're even a solid. And also if they're solid, they tend to be brittle. Think about graphite. It's strong in one direction, but you can actually break it really easily and shatter, and it's very brittle. And they're poor conductors. That's actually why a lightning bolt has so much power to it, because it takes that much power to bridge across the air full of non-metals, nitrogen and oxygen primarily. They are very poor conductors, so it takes a lot of electricity, a huge charge, before it can finally discharge across that distance. If air was a better conductor, lightning bolts wouldn't be quite so powerful. However, they'd be a lot more common. And they can be a solid, a liquid like bromine, or they can be gases like oxygen. All right, moving on to metalloids. Like I said, metalloids are everything that touches the staircase except for aluminum. And they have properties, because if you look at aluminum, aluminum's pretty shiny. It's a good conductor of heat, those kind of things. So it has metallic properties. So these generally tend to have properties of both metals and non-metals. So here's a picture of arsenic. It's got a little bit of shine, but not too much. Like if you can find a silicon. Silicon has shine to it, but if you hit it with a hammer, it's brittle. It's going to break. And it's also a semiconductor, meaning it conducts electricity under some circumstances, but not others. It's not always a good conductor. So this transition from metals to non-metals is not really all that instantaneous. And so the list of metalloids can vary, as you can see here, that the green ones, which are the ones I included on the list I gave you, are the most commonly accepted, 93% of the time. Sometimes polonium's thrown in there. Sometimes, actually I threw polonium in there on mine. That's one I've seen a good bit. Acetine is sometimes. And then every now and then people throw in these other ones. But for the most part, the green ones are the most commonly accepted as metalloids. Alright, so that gives us the history and the structure of the periodic table. And we will pick up with all the properties of these groups in the next video.